All right, are we live on the mic? Yes, we are. All right, so everyone having a good build so far? Lots of cool stuff? Or everyone's like, I was up late last night, I made it through the keynote, stop asking me questions. That sounds more like it. All right, so I want to borrow an hour of your lives that you're never going to get back to talk about all of the interesting things that go on when you build services on Azure that are intended to deliver value to somewhere between a small and a very large number of connected devices. We might call it an IoT style pattern, we might call it connected devices, we might call it just some fun software to build. I don't put too many labels on it. So just to set some context, my name is Mark Sims. I work for the Azure Customer Advisory Team. Essentially what we do is work with customers, internal and external, to build out some of the more fascinating systems that have been built on Azure. The content of this talk is drawn from experiences having built probably about a dozen, somewhere between a dozen and 15 different systems on Azure, ranging from 3,000 to 300 million devices. As you imagine, those two look a little bit different on various ends of the spectrum, but the interesting part is the patterns and many of the challenges are largely the same. So what I wanted to do is take a synthesized scenario. It's made up from the sins of several engagements, walk through a bunch of common anti-patterns, and then flip it around and explore with you guys what some of the choices and some of the implementation techniques you can leverage to not have learning moments at 3 in the morning in front of customers, because those are always really exciting. All right, this is going to be a lot of code in this session. If you are allergic to the sight of Visual Studio, for your health, I recommend you leave now. You will be seeing a lot of it with me. Was anyone in my session yesterday? Okay, so I'm going to spend very little time on the anti-pattern stuff because you already saw it, and then we'll dive into better ways to do things. I'm not going to pretend they're awesome, but they are at the very least less bad than the defaults. All right, sorry, yes. This is a smaller audience, intended to be interactive. Yell it out. I think we're small enough, I'll end up repeating the question, or feel free to use the mics. Remember, if you don't heckle me, I will heckle you. And I probably have more practice, except for Robin. You're welcome. It is. All right, so focus is not so much on devices, how to build firmware, how to do embedded design. I can talk about it, used to do it, but not as exciting. Really want to talk about what are the back-end services? How do you, sling out endpoints, receive connections, manage data, process it into something sensible? And what are the various implementation patterns and the choices you get to make between scalability, availability, and when do we ship this thing ability? Just made that up. And I'm going to show some stuff, and you may be looking at me going, no, really, that's happened? But we all know, and I'm guilty of almost all of these. When you're working on a deadline, you're pushing hard, sometimes like, all right, we'll just get it done. Or, nah, that condition will never happen. That's too many weird things that would have to happen at once. We don't have to worry about it. Well, sometimes you get lucky and sometimes you don't. And when things at scale tend to not get lucky, my team gets called. So we're going to share some of that. Really going to focus on 3 aspects: end-to-end asynchronous data flow and some of the gotchas involved in that. HTTP-based connectivity, which is good for larger devices that have a little more substantial processor and a richer stack, ones that have an operating system. For example, if I'm designing essentially an embedded device with a real-time operating system, I probably might look for something a little bit lighter weight than HTTP. As well as, if you're going to do queue-driven message processing, what are all the things that go into doing it efficiently at scale? That last one is probably the thing I've spent most time on in the last year, finding all the different ways to, I wouldn't say mess it up, but all the different ways to have barriers in terms of running at the scale that you need. So we'll spend a lot of time there. Seem reasonable? No one's running for the door that I saw, but the lights are on, so I can't see anything. Right? Nods? Yeah. All right. If none of this sounds interesting, there's a lot of other cool stuff going on, and we didn't lock the doors. So, indeed. So, funny enough, from all these different engagements, some ranging from the very sophisticated and very complex down to the relatively simple, every single one of them turned out to have the same core architecture at the heart of it, with in various forms of implementation. It's a really weird world of devices out there. Everything, especially the devices tend to get built before the services, or they tend to get built completely independently and the teams don't talk to each other. Because, why would we talk to people building something we need to talk with? That's crazy. So the concept of having this grand, unified, magical ingest service that could take anything works in a constrained domain. For example, if I'm App Insights, I can stand up a general front end and say that if you want to communicate with me, if my own clients want to communicate with me, this is the protocol you have to use, this is the authentication mechanism, this is the serialization format. Works great. Firmware is expensive to change. Applications can be challenging to update, especially if it's on a device that requires a user to accept your new update, which means you have a couple choices. You can be like Xbox and say, you don't update, you can't come and talk to me. Or you can say, if you got an older version, we'll still understand your data. So there's some interesting challenges there. So for most applications, and especially when we're in this nascent world where the standards for how to communicate are still evolving, you're almost always going to end up having to build some form of custom front end, ingest, or protocol gateway. Even the engagement was on about a month ago. They'd implemented REST. They liked it so much they decided to build their own version with custom HTTP header verbs, sending around packed binary protocols and then calling it REST. This is the norm, not the exception. There's a lot of weird devices out there. And for many good reasons around the complexity of building in embedded systems, bytes on the wire, all manner of things. We're not going to get nice, clean JSON payloads from a lot of embedded systems. And there's kind of, from there, there's a couple ways to build it. You can do direct coupled systems, where I'm going to take a message in, and I'm going to immediately invoke some business logic. We'll start with that as the anti-pattern. And the reason I call it out as an anti-pattern is it couples together pieces of the system and also locks you out of doing things you haven't thought of yet. One of the other things we see again and again is that these systems evolve rapidly. You establish the baseline where I can have a device connect, I can get some data, I can store it, I can run some basic logic, but then I want analytics, I want big data, I want machine learning, I want to be able to publish data feeds out to my partners. And if you have a direct coupled architecture, every time you bring on a new consumer, a new workflow, that's another piece of software that has to plumb all the way through the system and touch a lot of connection points. So we generally look at a brokered messaging architecture and any number of implementations. I'm just going to talk about one here today. It's a great session by Todd, who's hiding in the back there somewhere, yesterday on doing similar things with Service Bus. I'm mostly going to focus on the patterns in one implementation. It's just a matter of kind of how do you map your technology down inside these boxes. And then I'll talk a little bit about message processing, which is generally the core workflow when we think about these things of device is going to send an update, I'm going to update some durable store, I'm going to do some stuff. And I won't spend too much time on the bulk storage and latent analytics. It's more of a, if you can establish the core flow, this is a nice add-on, but you've got to set the foundation first. I've also explicitly differentiated embedded devices that tend not to have an organic in the loop, like usually a two-legged organic, from mobile devices, which will generally have a human interface. And mostly going to talk about the top line. Okay, so sample application. I'm using the same one from yesterday because, well, I like to reuse content. I'm a lazy developer that way. So imagine it's a world where I have a few thousand fast food outlets that are continuously publishing essentially 5-minute increments about their activity. Orders, dwell times, all that interesting stuff we can use to drive BI. And say that the point of sale devices have been configured that they upload to a central server every minute, say around the order of about 5K XML, because that's what the point of sale device is supported, and that's what you're going to get as the service developer. Seems really simple, but there's a bunch of stuff implicitly baked in here. Let's kind of tease it apart a little bit and think about some of the weird things that can happen. These devices already exist, and they're probably really, really expensive to change in terms of firmware, in terms of publication. Because if that thing goes down, that store is offline. And BI is cool, but if I can't sell whatever it is that I'm selling, my business is down, and I am profoundly unhappy. And if I'm, especially in a franchising market, if I'm profoundly unhappy as a franchisee, that can have more interesting long-term impact. So we pretty much have to accept whatever those things are going to give us. They're generally going to be store and forward based. The internet, strangely enough, is not perfect. It tends to break it in small pieces from time to time. We've never seen that, right? So most of these systems will be built as store and forward buffers. Well, they'll gather data locally, batch it up, and then try and send it. And if I can't send it now, I'll just hold on to it for a while, and then I'll send it later. For a few thousand devices, this isn't too bad. For a few 100 million, this is pretty terrifying. You get an inrush effect, where I go from getting that nice, steady metronome of data every minute to all of a sudden I had a major network outage for 10 minutes or an hour in one metro area. 100 stores go offline, wake back up, and because the firmware didn't take into account the ability to handle back pressure, they all start flooding the service. And I go from, say my nominal load is 100 messages a second. I go from there to 10,000 messages a second all at the same time. How do I deal with that? Do I do it gracefully? In our first implementation, no, we won't do it very gracefully. I may not even be able to trust the sender time. What if those devices aren't actually synchronizing timestamps? They're going to send me data that's completely bogus. And I can't use arrival time because they're batching. I may have been sent the last day's worth of data. And if I just say, oh, I'll just use arrival time because I can control that, I'll go, well, we sold 27,000 queso dips in 3 minutes. That's kind of cool. Again, the data can lie. You can't necessarily trust what's being sent, even though it's coming from a valid sender. So there's a lot of little interesting things we need to tease apart. There's a bunch more. I could talk for an hour about the challenges, but that's not very exciting. Let's talk about some of the things you can do, at least at the physics level. All right. So this is the implementation I'm going to walk through, where we have front-end Azure web role acting as the protocol gateway. Shoveling stuff into Azure queues. This locks me out of a couple, it's simpler, but it locks me out of a couple of opportunities. Azure queues give me a basic message exchange pattern. Cooperating producer, competing consumer. Meaning I'm only going to get only one entity is going to get a copy of any individual message. Meaning if I wanted to tee off some data and shovel it into storage, can't do it very easily. I'd have to bake it in. I'd have to couple that together in my business logic. So if I put in something like Service Bus and used a topic instead of a direct queue, I could then have that n-way communication. But this gave me less code to walk through, so we'll start here. And then on the back end, I'll have a worker role that'll basically light up, pull in messages, do a bunch of processing, and shovel it out into SQL. Pretty standard stuff. Let's now just dive in and think about where are all the little bits of fun we can run into. Skip past that one, I'll come back to that. So we already talked about there's a wide variety of protocols, schemas, and data types. I'm going to do 2 implementations. One where we get a nice XML payload that we can process. Another one where the device just sends me some packed binary, and I have to sort it out. Firmware is fixed, must conform. This is really not very fun. It turns out that this is actually one of the hardest challenges when you discover things about firmware. Project I'm working on now, I found out last night that we started off, we've been doing a rebuild. We've been doing it for about 3 or 4 weeks now. And we figured, all right, you get a message from the device, you queue it, you process it, everything's great. So far, so good. We're feeling great about the world. And then someone pokes up on a status meeting last night going, oh, by the way, we forgot to tell you. Messages have to be processed strictly in order per device. If it gets out of order, we can crash the device and brick it. And I'm like, I'd love to see who signed off on that firmware design. But this is the reality. I worked with another customer where if you created 2 inbound connections to a device out in the field, it locked it solid, and someone had to get into a truck and drive out in the middle of nowhere and reset it. Embedded devices are fun. And by fun, I mean exciting at 2 in the morning. I already talked about the need for a custom protocol gateway because you're going to snap to any number of protocols, perhaps concurrently. Because if I've got multiple versions of a device, and I will have multiple versions of a device in production, I'm going to need to speak any number of different protocols and schemas. Message versioning, this is always a fun one. If a firmware, depending on the version of firmware, it may send me different payloads. And some folks don't take into account versioning, so you have to do it forensically. Some create a new data type per version. That's really manageable. And the more sophisticated ones that are either invested in a type system or leveraged in an extant type system, like protobuf or thrift, have that baked in. So versioning's fun. All right, so ingest. I very rarely get to instantiate outbound connections. The world is full of network, firewalls and network Azure translation. It's kind of a mess. So it's almost always devices connecting inbound to my service so that I don't have to figure out where they came from, and the whole firewall thing is their problem. This has a really interesting impact on push notification. If I need to do low latency, interactive push down to the device, and there's not an active socket, I can't get one until it shows up. So for a class of, so if I'm working on something where I need to basically be able to notify an embedded device that doesn't have a back channel like a cell phone, within, say, a few hundred milliseconds, its firmware has to be configured to maintain connections. That's kind of a fun one, which comes back to socket management. If I need low latency push notifications, I have to hold sockets open. And sockets are a metered resource, so that gets challenging. what protocol am I talking, and this is tends to break down a little industry specific. This is kind of the split between a smart device and a less smart device. I don't want to call it a dumb device because they still do pretty impressive things, which is, do I have a full network stack and an IP connectivity on the device, or do I go through a concentrator or other accumulator? If I'm doing, does anyone have like a smart meter on their house? So those don't connect directly. Since they're using power line protocols, you don't exactly want that thing opening up a TCP socket over the wires outside your house. So they're going to go from a power line protocol to basically a head-end node at either the local substation or upstream, where you'll do a protocol conversion from power line to IP. And so all the things I'm talking about here also happen in these accumulators. The delta is, do I build my service to take 1 million connections from 1 million devices, or do I build my service to take 10 connections from 10 things that are metering 1 million connections? Do I have 1 million little ones or 10 really big ones? It really comes into the physics of how I design things. And what's my message response? Do I need to be able to go in with an interactive process, like, hey, unlock this car door? That would need to be interactive. That's not something that's really viable to queue and act on later, unless you want things to happen as someone's already gotten in their car after getting angry using the key and driven down the road, and all of a sudden it starts locking and unlocking. Not a great customer experience. For most things, I will be able to queue and act on them later. All right. The reason I push so hard on queue-driven message processing is most of this stuff is bursty. It's unpredictable. Things will move around in time. You're not going to lock down. The funniest one I've seen, and this showed up a few times, all right, everybody send at the top of the hour, which means everybody sends at exactly the top of the hour. And for 1 minute every hour, I have an enormous amount of load, and the rest of that hour I have nothing. This can happen deliberately because of less than optimal firmware choices. This can happen accidentally when you have enough devices that kind of basically phase lock, and I'll end up accidentally sending at the same time. Or it can happen because of store and forward effects. So I need some way to smooth out that load so that I basically don't end up breaking under the strain. And we'll dive into queue-based processing. All right, so I'm going to take 5 minutes, because most of you already saw this one, and talk about the less than optimal. And then I'll probably end up spending the rest of the time in Visual Studio going through stuff. Feel free to mock my coding, because this was just intended as a sample, and I deliberately left a few things out just to see if either you guys or I was paying attention.
Can you show us your database password?
Yes, but not here. I'm going to end up deleting the database anyway. So this is, for all intents and purposes, this is what I saw when I showed up at a customer about 2 months ago. I've cleaned it up, I've reduced the amount of code, but this pattern was largely in place, that I'm going to post a bunch of stuff from a device. So I'm using Web API, so far so good. And if the data's not validated, I'm just going to crank back an exception. So this is one of the very first interesting anti-patterns. Remember when I talked we had multiple versions of devices in production? What if I missed one? What if someone did an update of a firmware before I got to it, and I didn't know? If we're one of the kind of key aspects is I can't just take data and throw it away. I need to log this. I need to log it in a raw form to say, well, is there a rogue device out there? Did a firmware update leak out early? Or do I need to add a new message handler and reprocess this data? If I'm not capturing the raw context and logging it to something where I can go back and look at it later, I have no idea that, oh, we had a bunch of errors. No, those were perfectly valid devices. We just missed including a new message handler. And the reason I really don't like when I kind of pin on this one a little bit is it's one of those class of problems that you didn't know you had until someone physically complains. It's not necessarily going to show up as an exception, especially if it's swallowed silently and just thrown away. I've seen that one too. We've really got to have that raw data available to noodle over. Plus, it makes it easy to build test cases. And some of this is just good coding practices. Let's just put everything in one class because it's easier. I don't like navigating through Visual Studio. Can't make this stuff up. So, rate leveling. 2 ways to do it. You can do it right by introducing queues, or you can just randomly sleep in your code to say, I'll just wait and for the database to wake back up again. Funny enough, synchronous retry handlers cause exactly the same behavior. Unless you're implementing a thread break, unless you're implementing an actual queue, the kind of the games we play with retry handlers, they'll buffer against transient events. They will make the problem worse. Because basically it's well, I've tried, and now I'm trying again. and now everybody else is trying again. There's no way to bleed off the pressure. Of course, no one here would ever hard-code a config value, right? We all have. Let's be honest. We have all done this at some point in time, hopefully just on prototypes. This one, the fact that I had to put this one up kind of makes me cry a little bit. All right. I'll skip past the not doing async stuff and not wrapping stuff in a data access layer. Separation of resources. If I log back into the same resource that I just used that has failed, I have a problem, meaning that I had one problem and now I've created two problems, where I've just failed twice on the same resource and I don't know. Your logging system, your monitoring systems are incredibly important for live site operations, and they have to leverage independent resources. Now, I don't care if it's a database on a different cluster, even though relational databases don't make the best, just physically, they're not the best for high-speed bulk logging. It can be a different storage cluster. It can be just about anything. And you'll probably have a multi-layered monitoring strategy. But logging into the same place that you were just generated errors from is horrendous. Plus, doing direct logging rather than logging via policy is evil. Sheer, unadulterated evil. But I'd have to say, this is the one the one line, the one little teaser that kept me up later than anything else in the last year, trying to go, I know there's an exception somewhere in this 3,000 module system, but because someone kindly ripped the call stack out, I don't know where it is. So as we move to kind of task-based async with a lot of Lambda functions, one of the interesting aspects is if I throw the call stack out, a lot of times the exception will bubble as, here's the generic method wrapper that was doing timing that gets called for everything. So you go, any one of 300 different places could have called this. Okay, this is going to be painful. So luckily, things like ReSharper, which I used to hate, but I've become lazier in my old age and realized that it saves me from a lot of trouble. If you can't read that, it basically says exception rethrow possibly intended. They're very nice. What ReSharper probably should have said here is, why are you throwing the call stack away? Don't ever do that. So this common anti-patterns doesn't matter if it's cloud services, an on-premise application, a mobile app. A lot of these are just bad. The challenge when we get into a cloud service with unpredictable load is that the impact of these is magnified. And then when things go bad, they go bad a lot and very quickly and all over the place. And if you don't already have the mechanisms in place to bleed off the pressure, to provide good diagnostics, to help resolve the issue, it's already too late because by its very nature, it's going to be a public-facing service. And in this case, franchisees are like, where's my BI? Where's my real-time data? Help me manage my store. So it's a nice way of saying the things you didn't think of become visible to others very quickly. So let's go more optimal. I'm not saying it's great. Let's just say it's more optimal and talk about some of the patterns. So yesterday I was chatting about density. I apologize. This is not in the standard Azure Cloud Service template, and it really should. By default, Service Point Manager says I can open up 12, I think is the value we set it to in general, concurrent connections to the same URI. Great if I'm reaching out to a bunch of different endpoints. If I'm reaching out to a single storage account, I'm going to stack up behind that concurrency limit. So throttling good because we don't want runaway concurrency, throttling bad because I'm artificially limiting performance. At the same time, a lot of these conversations are very chatty, so I need to make sure that I turn off nagling to improve network performance. This should just be in the default template, and I hope to see it there in the future, but for now, you're really going to need it in there. This has a profound impact on the latency of storage operations, except for uploading large blobs. So let's just go and have a look at a slightly rewritten controller. So now what we want to do is we want to go from I receive and then process the data to I receive and then queue the data. So there's a bunch of things that have to happen here. We tend not to start here because it is more work. So I'm going to want to inject a data access layer because maybe I'll change the implementation. Maybe I'll run this in Mongo rather than SQL in the future. I don't know. But now I've framed out the door. I've left myself that option. I am a very I/O-bound application. I want to make everything async so that I'm not holding onto the thread while, because threads are a valuable resource. They are quite finite. Normally what I'd do is while I'm waiting on I/O, I'd at least yield the CPU so I'm not spin locking and creating a space heater. But in the brave new world, if I don't yield the thread, no one else can use it, and there's a finite number of those as well. So I want to be respectful as an I/O bound application. I want better density, and I want to go async end to end. This also lets me do things like bounding the time of calls. I'll show you how to do that in a second. So luckily, with 4.5, this is pretty simple. I say, hey, I'm going to return a task, and I'm asyncable, meaning that I'm going to wait on some stuff somewhere in here. So error handling is a fun one. There's a couple different ways you can do it. And for me, it really comes down to who has enough context to handle the error appropriately. So I can have one central interceptor that grabs all errors, logs them, shovels data out, and puts stuff back. Or I can do it on a per handler basis. In this case, I said, I'm just going to have one error handler. I'm going to plug it in using the ASP.NET delegating handler pipeline, and that should be good. Yep. So this one didn't change much. Ultimately, what we're actually going to be doing here is under the hood just calling the stored procedure to get data out. But posting gets a little more interesting. So rather than going with the default, which is Web API serialization and schema management, I said, I might need to get down to the wire here. Let me get raw access to the data. So I'm just going to pull out a message. And I can go and I can grab incoming parts of the REST query. Or if, for example, that device wants to put custom HTTP headers, I can grab them pretty easily. But if I get a bad response, I'm going to want to be able to record it somewhere. Because maybe I published a bad schema, maybe there was a firmware update. And after the HTTP socket has been established and I've posted my headers, I'm not guaranteed to have sent all the content, especially if it's a substantial body of data. If this is a few hundred bytes, statistically speaking, by the time I get to this code, the data has already been posted to the socket. But it may not have been, so that's an async call as well. I'm doing I/O, I want to be respectful. Yeah, your validation code should probably not look like, just give me some bytes. And then I'm basically going to use the same layer to, instead of processing the message, I'm then just going to go and publish the message. Pretty straightforward stuff. But this is where things get a little interesting in terms of switching from a direct system to a queue-driven, which is, oh, of course, that's an interface, so it's not going to find it directly. Is that I now have to go from a fully instantiated .NET type, which is probably a concrete type, to something that can be serialized and jammed in a queue. I don't want to take a dependency on any concrete types like HTTP request messages. I certainly don't want to serialize that and send it across the wire. I want to go to something that's a little bit more generic. So in this case, I'm just going to publish message T, take in my type, do a JSON conversion. If I was doing something for really high speed, if I wanted to do hundreds of thousands of messages a second, I probably would not use JSON, especially since I own both sides of that connection. I own the publisher, I own the consumer. This is actually wasting money. I would probably drop into something like protobuf for optimization. But if I'm only doing a few hundred a second, it's probably just a rounding error anyway, so I'm not too worried about it. Plus, it makes the demo a lot simpler because you can read the data. But one of the things is, my queue has a maximum message size length. Now, I assume that my devices will only send me 5 kilobyte messages, but maybe I don't trust them. Maybe I know the developers of the devices and I don't trust them either. Maybe I go, okay, there's actually a chance that once every 1,000 messages, I'll get a megabyte file when it dumps a debug log. So I want to account for that. So I'm just basically going to peel off the data, drop a copy into a blob, again, all async, and then I'll basically just put a reference into my message. Essentially, drop the raw content in blob, put a pointer in, throw that in the queue. And then I'll just drop my message into a queue, and off we go. And the same thing for there. So pretty straightforward, but there's one really interesting difference in terms of how my data access layer was generated. Explicitly move to a factory pattern that's returning a task of the object I'm creating. Because in order to initialize my data access layer, I have awaitables. Most of the time I see storage code written, you've got your create if not exists. Very important. Don't call it every single time. I've seen that couple times where we're looking at the performance against storage and storage is really slow. and we kind of take a peek at it. We dig down in the code and going, well, yeah, if you make 3 calls when you need 1, yes, latency will increase. You have to make sure that your metadata objects and constructs are in place, but this should just happen once. But that's an async activity as well, and it can time out. Say the storage cluster hiccuped, or you got the key name wrong. So the general pattern will be, I'll have a factory method that returns a task that I can then await on. All right. And from there, it's pretty straightforward. So the changes on the front end are pretty minimal. You're going to need a type system that can take messages and then render them down to something that can be put into any form of messaging system. You're going to need to go async end-to-end, and you're going to need to capture raw data and log it for auditing purposes, as well as to be able to run the system. Make sense so far? Pretty small stuff, all in all. But this is the kind of setting the stage for being able to absorb shocks and handle nasty bits of load. Any of this seem terribly unfamiliar, crazy? Wish we should have ordered more coffee. All right. I'm going to just flip over and talk a little bit about queuing. And I'm going to start with a simple queue manager. As you might imagine, this is just somewhere we're going to get started, and then we'll move something a little bit more complicated. Generally, always recommend separating the code that gets messages from the code that processes messages. You definitely want really good separation of concerns there. Otherwise, you have this one ball of goop, and when you start having errors, is it an error because I couldn't pull messages fast enough, or was it an error because I couldn't process them fast enough? Todd will laugh shortly at this one. I was working with a customer about last year who was complaining that one of the service bus, because I'll call it out in a really good light here, was running really slowly. It was only doing like 6 or 7 messages a second. And I'm thinking, well, that's not right. The way that they built the system was that the code that pulled data off of a service bus topic and the code processed it were essentially one class. So when they were doing timing, they were timing the whole thing. Kind of the performance of the messaging system from the performance of message execution. And there was a block, there was contention in message processing. So what was happening was, if you ask a system for 6 messages a second, you tend to get 6 messages a second, strangely enough. But because the things were coupled, the telemetry was for the intact thing, rather than having enough granularity to go, no, we actually have a blocking contention issue in processing that we need to work around. So, same kind of deal. I have a simple queue manager. I don't care if you do this with Lambda functions or if you do it with inheritance. Just have the ability to pass in a message processor to say, you will give me messages, I will do something sensible with them. Same kind of deal where I have to initialize some stuff asynchronously. All right. Let me zoom in on this one because this one's a little complicated. So I want to use a long-running task to basically pull data out. A couple of interesting things going on in here. The function is itself explicitly asyncable, so I can await any kind of pulling on messages, and it's long running. But I've explicitly pinned on a continuation token to handle errors. This won't save me from missing a code path and tripping an exception. What this will save me from is having an uncaught background exception just float out. I've seen a number of systems brought down by having unawaited tasks that did not handle errors properly. So basically, you guys are familiar with how tasks do exception propagation? A couple of blank looks, including mine. So the great thing about tasks in the world of concurrency management is that they do handle exception marshalling. They will get it back to something that's waiting on the thread. The challenge is, and so if I go await something and it turfs an exception, I will get that back. It won't disappear on a magical background exception or background thread exception that's almost impossible to debug. So that's the good news. The bad news is when I do want to spawn something off and just let it run where it's not awaitable, something's either got to register to receive that fault, or the system's going to get brought down. We don't want that. So in this case, I'm just going to say, hey, if this thing faults, just call an error handler. And the only thing I have to watch out for in the error handler is if I don't basically call get on the exception property, the .NET framework goes, you didn't really take care of that exception, I'm going to blow up now. So I've seen folks actually register the fault handler and then not check the exception property. And then your site's down, or actually your back-end processing is down. Kind of the flip of that is, even if I lost the worker, I'm still actually fulfilling my primary workload of receiving data from customers. Another good reason to mediate through a queue. So reasonably simple, basic queue handler. While I'm waiting for it to be canceled, I'm going to grab a couple messages, or actually I'm going to grab a message, I'm going to do it async, and then I'm going to process it. Okay, so what's wrong with this? There's no syntax mistakes. This will actually run. But throughput-wise, I'm going to go, basically, it's like going to the store and getting one egg at a time. I'm going to go, I want to get as much work as I can get in a single trip and then process it. Since storage is metered on operations, not on how much I get out in each operation. So I want to maximize each thing. I want to be chunky, not chatty. So let's just go and say, hey, let's get some messages. Get messages async. And I can get 32 in one shot, so I want to get as many as I can. So far, so good. So if I have any messages, let's process them. And then for each in messages, right, so far so good. So, what'd I miss? What happens if there's no messages? I go, well, there's no messages. Let's ask again, and again, and again. This is a space heater. This is the most common space heater, which is if there's no work, no, really, I want more work. Now, storage transactions don't cost all that much, but they do add up, and this is essentially throwing, that without a wait is throwing money away. And it'll pin one of your CPUs to 100% every time. Just because I like to have the explicit else statement. So say if I backed up in the queue, and I process through a bunch of messages, I want to go back immediately. I only want to back off. Oh, sorry. The question is, why did I basically check for any before doing a for each? Because I want the else statement that says I will only await if there are no messages. Otherwise, I'll get a bunch of messages and then stop, and get a bunch of messages and stop. And then when I look at my throughput graph, I'll see these little blips on the end of each successful message pull. That's all. So then I'll just put in await, task, delay, 50. Okay, so far, so good. Seems reasonable. What else am I doing wrong? Sorry, what was that? Yeah, great question. So the question is, can I do process func in parallel? Absolutely. So think about a world where, and this scenario is not directly applicable, we've got other ones that are, where the processing of messages is latency sensitive. So this is essentially saying I have one thing processing messages, and everybody gets in line, and we process one at a time. So if any one of those blocks, it's going to block everyone else behind them and cause latency to spike. So I'm assuming that maybe I can actually do a certain number of these in parallel. So let's do that. Let's fire up some work and do that. Task.run, process func, and I probably, there we go. Okay, and then just boom. There we go. Okay, so far so good. This is horrendous. This will blow up your machine. The question is why? What will happen here? Sorry, that's...
You will receive all messages and start processing in time.
I will receive more messages than I can process. This is unbounded concurrency. Anytime you have truly unbounded concurrency, in conditions of success, you'll become unsuccessful very quickly. So if I can complete all of those all the processing of all of those messages before I can go back and get more, great, it'll be phenomenal. Of course, we all know that that never happens. I'll have one of those block, and then I'll have two of those block, a certain type or a resource, and all of a sudden I'm going to have tens of thousands of tasks just hanging out, and well, then I'm going to blow up. So we've got to bound concurrency. We've got to have some form of constrained concurrency. So let's constrain concurrency. Let's wait until these are all done. So I'm just going to say, all right, I'm just going to have a list of tasks. And then I'm going to add some of those. Seems reasonable. We'll get to that one. So the question was around a parallel for each. We'll get to that in a second. I want to do one more bad thing before we get to the good thing. And I'll wait on all those tasks. Oh, sorry. Apparently I'm faster than IntelliSense today. Okay, so far so good. Now my concurrency is bounded to 32. I will never have more than 32 tasks pending at any given point in time. And if I did this with the parallel, using the kind of the parallel execute, I could make the number different than 32. There's one last optimization left here.
Well, you'll never have more than 32 tasks running at any given point in time, but you'll most likely have less than 32 tasks running at any given point in time. So when one task is done, you might just go for another one.
Exactly. So the statement was, as one task finishes, why wouldn't I want to spin up another one? The challenge with this is I'm not prefetching data. I'm not basically looking at a high and a low watermark going, hey, if there's 3 tasks left in the queue or 3 messages left in the queue, I should go get more. So by the time the things that are processing are done, there's work available for them. And the reason why I did Azure queues rather than Service Bus is if you use Service Bus, you don't have to see any of this code because it's there for you. But these are some of the considerations that go into low-level message processing and being able to bound and handle concurrency. So the queue manager, which implements concurrency, looks a little bit like I've got one task pulling messages, and I've got n tasks processing. And I wouldn't use parallel here because that's intended for tasks that basically have a start and a stop rather than a continuous. So pull messages looks the same. I just jack them into an in-memory queue instead. And then for executing them, I do something a little bit more interesting. Has anyone ever used the blocking collection capability in .NET? A couple hands. So one of the really neat things introduced in .NET 4 is I have a queue, and I want to be able to shovel stuff into it, but I also want to be able to read things out of it. I don't want to basically sleep while there's nothing in it, and I want to be able to have clean cancellation without having to do thread aborts. So this little thing called a get consuming enumerable is probably, until async await, this was my favorite thing in .NET. So I can take a blocking collection, which is a concurrent queue, I can put a consuming enumerable around it, and then I get an IEnumerable that if there's nothing in the queue, no work happens. And if I need to basically stop processing for clean cancellation, I just activate the cancellation token. It's my little hidden gem in .NET. So anytime you have to do any form of kind of in-memory queuing, this makes pulling data out so much simpler and a whole lot more efficient than the while true queue messages dot count greater than 0 get stuff. So get consuming enumerable is your friend. Poison messages. I'm not always going to get the message processing logic right. People are going to send invalid data. And if you don't basically detect things that you can't process, that you've tried to process before for whatever reason, and get them out of the way, they will eventually predominate the system. So most queuing systems will have a way of saying, how many times is this thing being dequeued? And if that number is too large, it's a safe bet to go, something's wrong here. Let's just get it out and put it on a different processing path. So I didn't finish the code here, but normally what I'd do is I'd take the message, I'd push it into blob storage or table storage, flag it with any sort of contextual data, and then just have a periodic process that would go through and look for these things. Similar to how if we got bad data at the front end, we'd shovel it into an archive to look at later. This is the same concept. So, and then we're going to go and we're going to process the function and delete the message. Now, normally I want to time every single execution through the system, so to be able to understand the performance on a per message handler basis. But I don't have any context as to what that message is right now, so I'm going to have to let someone else do the timing. I'll just dig in a little lower and talk about a dispatcher. I have seen this particular pattern implemented, I don't know, 50, 100 times. They all look largely the same. You're going to have a handler, a class that knows how to take in a message and do something. You might identify it with an attribute. You might identify it with convention via a name. That's how Web API works. You might do any number of things. I did an attribute-based implementation. And again, The only thing to watch out for in this particular world, and I'll show you why in a second, is that async await is amazing in that it let us put so much more work through a given instance in .NET. The flip side of that is it let us put so much more work through an instance of .NET, meaning that interesting things around concurrency and contention that would never show up when we were running slow, all of a sudden jump out and go, surprise, here I am. This happens to be one of them. If I have a system that is, say, using a dictionary, just a plain old bog standard dictionary, and I run 10, 15, 30, 50 messages a second, no problem, works great. If I run 5,000 through, instead of doing processing, my code will bottleneck on trying to retrieve a handler out of that dictionary. Every single time. And because you're mostly doing reads, there's no real reason not to use a concurrent dictionary here. So that's just a little free. This will save you a lot of pain and suffering. So again, pretty bog standard stuff. I look for everybody that's got a handler attribute and I register it. I grab a handler, an iMessage handler is pretty simple. It basically just says, oh, let's look at default handler. I'm going to process a message. And if I ran this in production, I get a message I didn't actually see. Of course, I would have problems because it would throw an out implemented exception. So all I'm going to do is I'm going to have a task, I'm going to get some data, and it's going to process it. But here's perhaps one of the most important things you will ever implement, in whatever form you choose to implement it, is for every given type of message, I'm going to time how long it took to process it. And then I'm going to have an API somewhere that knows how to log timing information on execution. Now, whether you do this with New Relic or AppDynamics with a function intercept and a promoted property, or whether you plumb it indirectly, it's a personal preference. It just matters it's just how you want to go about logging. The most important thing is you get this data. And I'll show you a graph in a second as to why this is critical. I want to know what the method context was, and I want to know how long it took. I may add a few more things like what was the success code, because hey, I could process this particular message in 1 millisecond unsuccessfully every time. So the data is fairly important. Let me just actually flick back to the slides for a second and actually just show you the impact from some real data of some of these techniques, or more importantly, not implementing a couple of these. Okay. So this is a cutoff graph. I had to scrub it a little bit. Let's see if I can zoom it. Unfortunately, I don't know if I can zoom in too much here. Oh. Great, thanks, PowerPoint. Apologize, it might be a little hard to read. Essentially, that's the average min and max execution per task type. So what we would do is we would take that trace API data that basically said this method took this long to execute and look at variation. As soon as I see that swing between min and max, like that big swing, there's contention somewhere in the system. Some resource is blocking. It may be within the machine, it may be a downstream resource like a SQL database or something in storage. But as soon as you see this sort of thing, you know you have a code path that is hitting blocking issues. Or maybe it is actually itself a highly variable thing, or a highly variable execution. Maybe one time I get 1 kilobyte of data, another time I get 10 megs. But unless you have this data, you don't really get a sense of kind of what's going on. In this case, this was the dictionary contention. That's what was actually causing that variation, which is why I saw variation across all message types instead of just one message type. And here was the impact on a specific, on one handler. It ran, it ran, it ran, it didn't run, it ran, it didn't run, it blew up. We see this unbounded resonance curve anytime you hit a hard contention point. Everything's cool, it's great, you're more successful, you get more throughput through the system, and then kaboom. This happened in about 2 minutes. And once the system had hit that point at the end, it could never recover. There was no way to back off on that pressure. We basically had to reset the whole thing, and then 2 minutes later it blew up again. Good thing is we weren't losing data because we were getting into our queuing systems fast enough that was acting as that back pressure point. We just couldn't process data. Luckily, we found this 3 days before go live. So load testing is your friend. But here's the really interesting one for this class of application. There's almost always a really strict Pareto curve between the 3 or 4 methods that get called continuously. They're the heartbeats, they're the status updates, they're the things that happen all the time. If it's a car, it's a GPS status update. If it's, name your kind of IoT style of choice, you're pretty much always going to see one of these things. So when it comes to system optimization, you generally don't have to make the whole thing run faster. you tend to have to make 3 or 4 pieces of code run faster, which is why it's so important to separate the thing that pulls messages out of your queue from the thing that schedules them from execution to the thing that actually drives the business logic, because then you can time them and tune them separately. You've got to make your message processing and dispatching fast for all things. But if I have 300, most of the systems I've seen vary between about 30 and about 350 handlers, depending on the types of messages and the complexity of their interaction. If I can only pick 2 or 3 of those and double or triple or quadruple the speed of my system, that's not a bad engineering investment. But I need this data in order to know, okay, I want the location updater task in a GPS-driven system. I'm going to want to spend a lot of time making sure that's really tight. I might want to take any developer productivity enhancements like an object relational mapper on top of my database and just rip them out, because they were great so that I could actually manage to build the other 349 handlers. But for that one, I want the minimum number of electrons between me and getting the job done. Doesn't mean you throw it out for all of them. It means you optimize one of them. Whereas for the reports that get run once a day, suck it up, wait. If you don't have the data, you spend time optimizing on things that don't necessarily really matter. So this is all suitably anonymized real data, but this is just from one implementation, but honestly, every one I've done, the same patterns come back again and again and again. So that's good, I think. All right, last little bit of code, and then I might just start asking you guys questions because you're not asking me enough. So, yep. There's only one more thing I wanted to touch on. We got a bunch of code, we got a bunch of patterns and a bunch of code and a bunch of guidance out on MSDN right now talking about logging. I could spend hours talking about that, but I won't today. The one thing I did want to touch on was configuration. Because let's go and actually look at the implementation of the data access layer. And let's just have a look at this guy right here. So I'm doing one good thing and one bad thing in this line of code. The good thing is I'm not hard coding stuff and I'm pulling it out of config. The bad thing is, where is this thing physically stored? I'll save you from me having to click through Visual Studio. This is actually in the app config. Took the standard configuration, just rolled it out to the cloud. This is a really bad thing for 2 reasons. I have 2 different roles in my system, which means I have an app config and a web config. So no one's ever fat-fingered a difference between 2 config files before, right? Now, come on, you know you've done it. If I don't have a single source of truth that's basically one atomic place to edit config, I will make mistakes. I will have things out of sync. I will have what happened to me yesterday when I was prepping some of the demo going, where are my queue messages? Why is this thing not actually writing? The web role was writing over here, the worker role was reading over here, and I spent half an hour cursing at not having put enough telemetry in until I went and fixed that. Pretty much the leading cause of all, well, at least the top 3, cause of all cloud service outages, fat-fingering config in any mechanism. Well, what I should have done in this particular case was, rather than going and saying, I like app config, I've used it for 14 years, I don't want to learn anything new. Rather than dropping it into this and putting it here, what I should have actually have done is gone and put it into my role configuration. Wow, that was cool. And apparently I picked the one thing that would crash Visual Studio. All right. Sweet. I should have put it in here, because I can update this as a PowerShell command, whereas app config and web config, in order to being separated files that I have to try and keep in sync, are also immutable in the context of a PaaS application. Now, the good thing is the overlay that I was using, this little configuration helper, and whether you use this, whether you use that, or whether you use the cloud configuration manager as part of the SDK, doesn't really matter. What it'll do is it'll look in the cloud service first, and then it'll drop back down to the app config and web config for those more hard-coded values. So it's the last little bit of things. So I'm just going to flick back and just talk about a couple of key takeaways. Yeah. All right. This particular workload has some interesting challenges around scalability and availability, because there's a lot of weird devices out there. They tend to communicate in weird ways, and there can be very explosive volumes of data. especially for something that's gone viral. This is very similar to kind of building backends for mobile applications that get insanely popular. You can go from, all right, I have 1,000 devices at launch to I have 500,000 the next month. That's what success looks like. That's awesome. But at the same time, success carries an interesting price in your backend services in terms of being able to absorb load, in terms of being able to scale, and in terms of being able to survive interesting code paths. Most of the challenges I've seen in production apps here come from connection maintenance, data types, and management of interaction with the device, as well as the ability to efficiently process stuff in the back end. If you get the two of those right, and of course we'll be coming out with more patterns and better tooling, and really what we're talking about here is building stuff at the lowest level of the stack, rather than snapping on to something like the ISS service that I think we talked about today, that let you work at a higher semantic level. Now, regardless of who solves the physics problems, whether it's the platform, the service layer on top, or your application code, you still have the same set of things to deal with. Good news is, the right set of patterns, the right implementation, these, you can build some very scalable things on Azure. So, got about 3-4 minutes left, and I hope at least got a few questions triggered out in the audience. If not, I'm gonna start asking you guys. Everyone's looking at each other going, I don't want to be the first one. Yeah, the code samples will go online after I have a chance to clean them up and put even more really bad anti-patterns in the less than optimal sample. Yep, yeah, we'll get out through, it'll probably go out on MSDN code samples. Yep. Yep. How do I choose between, say, a storage queue and service bus? It's really easy. What's the message exchange pattern? So just kind of an architectural philosophy, I always like to go to the simplest possible thing that can get the job done with the fewest moving parts. If the only thing I need is cooperating producer, competing consumer, I will generally just go with storage queues. But also, if I have a storage-dependent system, it ties the availability points together. If I need pub sub, I'm going to go with service bus. Simple as that. And for this pattern, I'm usually going to lean towards service bus because I want multiple consumers of the data. I want one system to do message processing. I want another system to take raw data and dump it into storage for batch analytics and HD Insight. I want another system to do live stream analytics using Storm. And if I go with a pub sub engine in the middle, then I don't close the door. I don't have to change code. I just add another consumer, as opposed to going, okay, now I need one thing to read from an Azure queue and post it into another Azure queue, and it gets messy. Once you get into that layer, once you get into that kind of stacking abstractions and stacking complication, it means you probably need to swap out one of the components with something higher up in the stack. Make sense? Oh, come on, Todd. You don't get to ask questions here. Service bus GPM. So Todd was talking about the, in addition to having kind of higher order message exchange patterns, Service Bus also has a number of protocol enhancements around things like batch and prefetch and not using HTTP if you don't want to, which when we get into the higher volume messaging scenarios really starts to make a difference. All right. Anything else? All right, fire away. Oh, someone's going to use the microphone. That's cool.
If you're using topics on the service bus and a web role has a subscription to it, and web roles come and go away, devices that are connecting to them, it may be different web roles each time. If you're dealing with multiple topics, and if there's a message sitting for a device that might end up in any web role, what's a sort of design pattern to be able to get the right message from the right topic if web roles come and go and devices connect to different web roles?
So there's really, I didn't touch too much on this one. The pattern that the question was around was, assuming that I have, say, 1 million devices out there, and I want to get a message routed from the backend system down to the individual device, how do I physically implement that, given that the thing that's basically standing in between, the web role, is transient and can come and go? We should do a Channel 9 video on exactly that. Because it's a fairly extended discussion in terms of how you handle partitionality and basically how do you do affinity. It's quite doable, but unfortunately it's one that will require some diagrams and some code to walk through.
Okay, we had some thoughts on Azure storage tables or some other storage facility to have, the devices will always have some unique identifier, and a sort of a lookup of where messages are sitting for it. So any web role could just look it up in this lookup table sort of scheme.
Once I get to that kind of degree of complexity, because really what you're talking about is a very hard partitioning and affinity. You're basically talking about a locality problem, meaning that you need to affinitize a connection state with a message state. It would either basically look at doing it in the message broker with essentially partition spans, or for those of you who went to the Halo discussion yesterday, I might actually stand up an Orleans grain representing essentially a micro queue for the device, and then pin in a subscription directly against that.
Okay.
Doing it, it's very possible to do this essentially with storage polling, but it gets a little complicated in terms of edge cases.
Right, so if you're doing that kind of sort of request response, right, and the response is critical to that, should you still do a async task and await? Is that necessary, or just keep it on that single thread if I have to wait for the data?
So if I have an interactive response, I need to come out on this socket and then come back on this socket, and I've got to be in the loop. I want to minimize the latency there. There's a difference between, do I basically queue the work and process it later, or do I process it immediately? I would process it immediately, but I still would want to yield the thread on the service side using async await while I was waiting for whatever backend thing to happen. It wouldn't affect the fact that I was writing an interactive response. I just wouldn't write it as a queued response.
So even if it's immediate, you still want to do the task await?
Yep, just taking, the web guys saw some really interesting data where they took just generic web pages, flagged them as async, and saw a 3 to 4 times performance increase, just because it allowed the underlying system to manage resources far more efficiently. So if you have any form of IO-bound activity, you should be using async await.
All right.
Doesn't mean it's not interactive. It just means that you're not going to hold on to resources while you're not using them.
Okay, on the surface it would seem creating that thread, you would take a hit on that as opposed to just get the work done on the thread you're already on.
But remember, tasks don't create threads. Tasks bounce in and out of threads.
Gotcha, okay.
Right. So I think we're already over, but I'm happy to hang around and answer a few more questions until the next speaker kicks me off. So thanks for coming.